Chapter 6 talks about a few additional chemical bonding theories, such as valence bond theory and molecular orbital theory. We're just going to cover valence bond theory. So everything we've done so far has been building on itself. So we've talked about Lewis theory and we've talked about quantum mechanics, but we haven't talked about how they combine and how they are related. And some of the shortcomings of Lewis theory is that it's pretty good at predicting trends in properties, but it doesn't do a great job of giving numerical predictions, so actual values like bond strength and bond length. Right, because we know that like if I have carbon dioxide, it has this Lewis structure, but we kind of would assume that these bonds are created equally. It does do a good job at first approximations for information, but it doesn't give us actual bond angles. Doesn't quite explain that. Lewis theory also doesn't help us write a one structure where we have resonance available. So we have to write multiple resonance structures in that case. And it also doesn't predict the magnetic behavior of molecules. So whether a molecule will show up as paramagnetic or diamagnetic. For example, oxygen is paramagnetic, but we wouldn't know it from its Lewis structure. And so we also talked about quantum mechanics. So the gist of valence bond theory is that bonds are going to form or occur when the orbitals on the atoms overlap or interact. And so the interaction will depend on what kind of overlap do we have. So do we have direct overlap like what I have here with our hydrogen atom, where the s orbitals are overlapping directly on an axis, or do we have something aligning outside the axis? So I'll show you what that looks like in a bit. The summary of valence bond theory is that, we have valence electrons that are showing up in these atomic orbitals we learned about. We learned about the s, the p, the d, and the f orbitals. But valence bond theory says there may be some kind of orbital where we have a hybrid of the various atomic orbitals. And a bond's going to happen when there's overlap between two orbitals that are specifically half filled, and they have pairing of the valence electrons in each atom. And sometimes we can have a different, but for the most part, we're gonna have pairing happening. And then ultimately, the geometry of our of the orbitals are what's going to govern the shape of the molecule. So before we just talked about electron domains, but now we're getting into those electrons domains being the orbitals. So if we think about something like hydrogen sulfide, H2S, we know that hydrogen, it shows up with a 1s1 electron configuration. Here's its orbital diagram. And sulfur shows up with 3s2, 3p4. So how we do its orbital diagram, it looks like we have a p orbital that is two p orbitals here that are half filled. And our p orbitals, if you remember, we have them on the y-axis, on the x-axis, and then this is coming forward and backwards on the z-axis. And so if I have these bonds happening, then I should have a 90-degree angle between those bonds. But what we actually see for hydrogen sulfide is a bond angle of a 109.5. So this shows that our quantum mechanic theory that we have so far doesn't align with what we see for the Lewis structures and molecular shape and geometry experimentally. So our main concepts again are that our valence electrons are living in atomic orbitals. They can live in regular old s, p, d, and f orbitals, or they might reside in hybrid orbitals. And our chemical bonds happen when there's some kind of interaction between the orbitals, and there's a spin pairing of our half-paired or half-filled orbitals. and the shape will be determined by the geometry of that. So once again, we have bonding with when our orbitals interact or overlap. And they must overlap along the axis, like I showed you with our s orbital, or they need to be aligned parallel to each other and perpendicular to the axis. So you'll learn about that type of bonding in a minute. The issue that we see, though, is that when we talk about atomic orbitals, this doesn't actually help us predict the number of bonds or the orientation of the bonds. We saw that in hydrogen sulfide. The bond angle wasn't what we see for that molecule. So to adjust for that, we're going to consider that we're going to actually hybridize or mix the atomic orbitals. So our sp DNF orbitals, we're going to mix them together and we're going to get new equivalent orbitals out. So if I mix the 2s and 3 of the 2p orbitals for carbon, I'm going to get 4 orbitals out. And those 4 orbitals would come together and form a tetrahedron, like what we see that carbon tends to do. So just showing what happens. So if we look at the molecule methane, it has carbon and hydrogen. What we would predict, we know that hydrogen is 1s1, and we know that carbon's valence electrons are 2s2 and 2p2. So if I was to draw these orbitals, what I would have for carbon is an s orbital. Let me draw it blue. An s orbital that's spin paired, right? That's this orbital. And then I have 2p orbitals. We'll just draw them. There's one on the y-axis and one on the x-axis. Okay, and they each have 1 electron in them. And so then if I have hydrogen again, going back to hydrogen here, it has a 1s orbital. And so the only possible place that it could bond would be on this one and on this p orbital. So the bond angle, well, the molecule would be CH2. I could only technically form 2 bonds. And the angle would be 90 degrees. But that's not what we see. For methane, we get CH4 with bond angles of 109.5. So let's figure out how we can combine our quantum, or adjust our quantum mechanics to get what we see in. So some atoms, especially when they are central atoms, they're going to hybridize, and that's going to help maximize bonding. When we maximize bonding, we're getting more full orbitals, right? Electrons filling them up, which means it's more stable, which I would also say means lower energy. So hybridizing is when we mix the mixing of different orbitals from the valence shell, specifically our atomic orbitals. We mix them together and we get new degenerate orbitals. Remember, those mean they have the same energy. So far, when we've had orbitals, like our 2s, is lower energy than our 2p. So we would fill up the 2s first. And now the 2p orbitals, these 3 guys here, they're degenerate. And that's why from Hund's rule, we're going to go spin up, spin up, spin up, spin down, spin down, spin down. Because they are the same energy. So we're always going to fill from lower energy up. And so different atoms, or some atoms, can have a variety of hybridization, and it just depends on what other atoms are combining with it. But the key thing is the number of orbitals that come in are the number of hybrid orbitals that are going to come out. So just so you know how this kind of works is when we have let's look at like an s orbital. We think about that mathematically, and you can go back to chapter 2 and look at this. But our s orbital is a sphere. So if we look at it mathematically, it kind of looks like a sine wave. One lobe, all one phase, all the same size, sine. But if we look at a p orbital, it has 2 lobes, so it kind of looks like this, where there's one side that's positive and one side that's negative. So if I were to superimpose or add those together, I would get something that looks, let me pull up a purple marker to show the mixing. I'm going to add these 2 positive sides together, and I get a much more positive a lobe, and then if I add these two sides together, I'm going to get a smaller lobe. So what we end up getting is something that looks like a little side here and then a big lobe here, and that allows for more overlap with our valence electrons, and so you're going to get a stronger bond. Where our original p orbital just looks like that. Okay, so when we have a carbon, in this case, it's going to combine the one of the 2s orbitals with 3 of the 2p orbitals here. You can see them. And it's going to give us 4 new orbitals out. So 4 orbitals went in, an s and 3p orbitals went in, and 4 sp3 orbitals are going to come out. And they're all the same energy. So we'll draw 1, 2, 3, 4, and we label all of them as sp3. Now the superscript here, so initially we had 4 electrons, right? And only 2 of them could bond because only 2 of them were half filled. But now we have 4 that are equal in energy, and so we can have all 4 electrons fill, allowing for 4 bonds to be formed. So the number and type of orbitals that go in will determine what kind of shape the hybrid orbitals have. And the type of hybridization that's going to occur is the one that's going to give us the lowest energy. That's why anything happens, is to lower the energy and make things more stable. So jumping in, when I have an atom that has 4 electron groups around it, we know this as tetrahedral geometry already. So nothing changed here, right? This has 109.5 degree bond angles. It can be our trigonal plane or trigonal pyramidal and bent shapes as well. And basically the atoms are going to use our hybrid orbitals to form bonds for all of the bonds and lone pairs. So what happens is 4 of these orbitals go in. I get 4 new orbitals out. 1 s, right, an s orbital, and then 3 p orbitals. So I'm going to write p3. We superscript with the number. So notice I'm going to have 1 s and 3 p's, meaning 4 sp3 orbitals come out. And because we have 4 electron groups, that's the 4 orbitals. So this carbon, because it has 4 groups on it, it's going to be sp3 hybridized. And each electron here for carbon will be able to fill up one of these lobes of the hybridized orbitals. If we look at nitrogen, nitrogen has 5 electrons. So when it gets sp3 hybridized, we're going to put those 5 valence electrons, 1, 2, 3, 4, 5. Notice one of them is filled. That corresponds to the lone pair that shows up on ammonia. And then these 3 atoms here, or 3 electrons, are the ones that are going to form the bonds with the hydrogen. Next we have sp2. So these are the types of central atoms that have 3 electron groups on them. They have trigonal-planar geometry, electronic geometry, and are trigonal-planar and bent molecular geometry or shapes. They have 120 degree bond angles and they're flat, right? So we're going to use these hybridized orbitals to form sigma bonds, and we'll use or lone pairs. And then our non-hybridized p orbitals are going to be used for pi bonds. Now you may be wondering what a pi bond is, and we're going to talk about that on the next slide. So what's going to happen for sp2 hybridization is we need 3 electron groups. So we need 3 orbitals. So we'll bond in here our s orbital and 2 of the p's, right? So we have 1 s and 2 p's for 3 total orbitals, 1 from the s and 2 from the p. Notice 1 p orbital didn't get used up, so it's still hanging out there. So we have our s orbital, our 2 p orbitals go in, 3 orbitals total, 3 orbitals come out. They look very similar to the other ones. When we connect them by their, like if we look at these like balloons and they have their like knots, hold them at the knots and they make a trigonal planar shape. So what is going on with our z p orbital here? So if you can imagine, it's on top of this trigonoplanar coming out of the whiteboard. So let's see what happens with it. So there are two types of bonds. First one is sigma, which I've alluded to already. This is happening when we have our orbitals pointing along the axis connecting the bonds. So we could have regular atomic orbitals, like when we saw with hydrogen atoms, right? Here's an s orbital, here's another s orbital. There's direct overlap. I could have a p orbital. So here's a p orbital, right? If I have an electron there, and another p orbital from another atom with another electron, and that's direct overlap. So that's another way to have a sigma bond. I could have an s orbital with a hybridized orbital like that, and that's going to be a sigma bond, but direct, strong overlap. Pi bonds happen when we have nuclei from specifically parallel p orbitals, so unhybridized p orbitals that are parallel to each other and perpendicular to the axis. So if I have two atoms that are bonded, let's say this way, with our sigma bond, and I have one unhybridized p orbital here, one unhybridized p orbital here, they're next to each other. So if they each have an electron, then they're going to basically almost like reach over on tops and bottoms and form a pi bond. So how the book kind of draws it is looking like this. And I don't like drawing it like that because it's, well, challenging and ugly. But that's kind of what it looks like, is a little like balloon or like a bun if we had a burger, right? Where the sigma bond is the burger patty in the middle with the strong force, and this extra pi bond is strengthening the connection. It's not as strong. Sigma bonds are really strong. There's a good grip between those orbitals. Sigma or pi bonds are not as strong, but they will strengthen the connection. So sigma bonds are actually stronger than pi bonds. But if something has a sigma bond first, let's say it has something that looks like this, sigma bond, and then it has two unhybridized p orbitals here doing a pi bond, that would be stronger than a sigma bond by itself. So when we have how we draw these diagrams is we show the overlap with our hybridized or unhybridized orbitals, resulting in a sigma bond. And then when we have our unhybridized p orbitals overlap, that will be a pi bond. You'll always have your first connection be a sigma bond. Any second or third bonds between atoms would be from pi bonds. So for example, if we have H2CO, then we would draw a normal Lewis structure. So we have two hydrogens, each having 4 valence electrons from carbon and 6 from oxygen, so for 12 valence electrons. Our Lewis structure would look like carbon, oxygen, hydrogen, hydrogen. We have 2, 4, 6, 8, 10, 12, but notice carbon is missing an octet. So we'll do a double bond. We'll move one of those lone pairs over to be a double bond. So we can see from this central atom, it is trigonoplanar, right? 3 electron groups. So if we looked from before, for 3 electron groups, we need 3 orbitals. So we're going to get one from an s, and we're going to get 2 p's. So this would be an sp2 hybridized orbital. And so what we'll have here, and this is going to be a little tricky, so I'll do purple for my hybridized orbital. So this carbon has an sp2. So this guy's coming out of the board, this guy's going behind the board, and this guy's in the plane. So, and then each of them will have an electron from carbon. Now hydrogen we saw, so hydrogen here has an s orbital, right, 1s1. So that will be that bond. So I just drew that bond and our oxygen. So if we look at oxygen's electron configuration is 2s2, 2p4. So we'll have our 2s orbitals and our 2p orbitals. 1, 2, 3, 4. So this orbital and this orbital here of my p orbitals are ready to bond. So I'll draw those as red. So let's have our oxygen here. So we'll have one p orbital here forming a bond, and we'll have one p orbital here that's unhybridized. Now notice for our sp2, we have one p orbital that was not involved in hybridization on the carbon atom. So we're going to be able to, so it's going above and below that trigonoplanar plane. And so what we get is a pi bond forming here between the carbon and the oxygen, and that is corresponding to that second bond. So the first bond was from our sp2 hybridized orbital and one of the oxygen's p orbitals, right? Let's say it's from that p orbital. And then the other one came from this pi bond. So that double bond was a pi bond. When we have a sigma bond, it allows for rotation, because if we were to twist or rotate that bond, nothing's going to happen, right? Those electrons and that atom is allowed to move. When I have a pi bond, though, they are locked in above, right? It's perpendicular to the nuclear axis. So if I try to rotate this guy around, it will break the connection, right? Because they have to be parallel to each other. So if only one of them is moving, it's going to snap that bond. So when we have pi bonds, the bonds actually get restricted. So we can see here two isomers, which are the same molecule but just a different arrangement of dichloromethane. And what happens is with the pi bond, it actually restricts the rotation. So the cis isomer means that the chlorine atoms and the hydrogen atoms show up on the same side, and are in the trans isomer, then they show up on opposite sides or different sides. And they are stuck like that. So how you draw it is actually how it is going to show up in its shape. So when we have an atom, a central atom that has two electron groups, we know that as having the linear shape, and it has a 180-degree bond angle. Now in this case, we're going to take one s orbital and one p orbital, right? One s and one p, and it's going to make an sp hybridized orbital. It's going to make two of them, actually, right? Two go in, so two of them have to come out. And notice we have two p orbitals that are not going to be used. So when we mix these two types of orbitals together, we get two sp orbitals, one like that, another one looking like that. So when we put them together, they almost kind of look like a p orbital. But keep in mind, this lobe is one sp orbital, and this lobe is another sp orbital. So you got two orbitals here, versus with our p orbital, we have that both lobes are one orbital. So when we have an atom or a molecule that has a linear shape, so I could look at that carbon and that carbon and say, okay, two electron groups on each carbon, so that's linear. Now we're also going to say that means it's sp hybridized. So we can see here with our purple, we have this carbon has two sp hybridized orbitals. This other one has two other sp hybridized orbitals. Again, the hydrogen atoms are going to bond, form a sigma bond. So how we would notate it is we say there's a sigma bond. It's between the carbon and the hydrogen. And you're also going to label which type of orbital. So the carbon came with an sp hybridized orbital, and the hydrogen is simply an atomic s orbital. So both of these bonds are that. Now the sigma bond between the two carbon atoms, right? So we write sigma between the two carbon atoms. Each of those carbon orbitals that overlapped were sp orbitals. So that's what we'd put in the parentheses. And then notice that we have, let me do this in red. We have one p orbital there from our carbon. This carbon has another p orbital, right? Two of them didn't get used. Now moving forward in front of the plane, we have a p orbital and another p orbital here. So we form two pi bonds between those two carbon atoms. So far we talked about linear, right, being having sp hybridization. We've talked about trigonal planar, right, 3 electron groups having sp2 hybridization, and we've talked about tetrahedral, which is harder to draw, right, but we have 4, this one's going out of the page, this one's going into the page, 4 groups having sp3 hybridized. But now we've run out of orbitals, right? S and p orbitals. We only have 3 types of p orbitals, 3 p orbitals in a level. So how do we have these expanded octets? Well, the kind of basic theory, which is questionable at this point in our lives, is that we tap into our d orbitals. And this would explain why only the 3rd row and below can have an expanded octet, is because we have the d orbitals available. So atoms that have 5 electron groups, we know those as trigonal bipyramidal electronic geometry. We know the molecular geometry as seesaw, as T-shaped, and linear. And we know that the bond angles are 120 between the equatorial position and 90 between the axial to equatorial. So we could pull in a d orbital from the valence shell, an empty one, right, and then use those to form sigma bonds or have lone pairs in them. And theoretically, those extra d orbitals can be used for pi bonds. So again, we have an s orbital coming in, 3 p's and 1 d, so 5 going in. We get 5 coming out, so that is our for 5 sp3d, right? 1s, 3 p's, 1 d, and then 4 of the d orbitals are still left unhybridized. Now with 6 electron groups, we know that as octahedral. Molecular is square planar, or square pyramidal and square planar. And those bond angles being 90 degrees. Okay, again, we are going to use empty d orbitals to form the hybrid orbitals and extra d orbitals to make pi bonds. So now we have 6 electron groups, so we have 1 from the s, 3 from the p, and now the extra 2 come from the d orbitals. So we get 6 go in, so 6 come out. All 6 are called sp3d2 orbitals, and 3 of the d orbitals here remain unhybridized. So that gives us our octahedral shape. Here is a summary of all of those. You can kind of add it to your chart with the all of the geometries that we did in the last chapter. Okay, so the steps for figuring out hybridization and the bonding scheme, and the bonding scheme is like labeling the bonds, like we did earlier, is you start by drawing the Lewis structure. Then you use VSEPR theory to predict the geometry, specifically the electronic geometry around the central atom. Then it says use table 6.1 to select the hybridization of that central atom, but you know, that's not that helpful. But basically, you just need to know, right? 2 domains equals SP. 3 domains equals SP2. 4 domains equals SP3. 5 domains equals SP3D. 6 is SP3D2. And again, we can add up the superscripts, and they should add up to the domain. So 1 and 1 is 2. 1 and 2 is 3. 1 and 3 is 4. 1, 3, and 1 is 5. 1, 3, and 2 is 6. And then you're going to sketch the atomic orbitals and the hybrid orbitals, showing the type of bonds, and then label the bonds as sigma or pi. Whoops. And determine like which orbitals are doing the bonding. So let's do that for bromine trifluoride. We do the same steps of counting valence electrons. So 7 plus 7 times 3 is 28. We'll do bromine, and then 3 fluorines, 2, 4, 6, 8 from the bond, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So we can see this is trigonal bipyramidal, right? 5 domains or 5 electron groups. That means we need 5 orbitals. So we're going to have 1 from an S, 3 from P, so 4, and we need an extra D. So how to draw this is we'll draw our central atom bromine is sp3 hybridized. So I'm going to draw that with purple. We'll have our axial and then our equatorial. I'm actually going to draw it here, the equatorial going straight and then into the board and then out of the board. Now I'm just going to draw these lone pairs right here going in this position right there. So there's our lone pairs. Now we have our bonds 1, 2, 3. And now let's deal with the fluorine. So that showed that orbital, and that orbital. So now let's deal with fluorine. Fluorine we know is has an electron configuration 2s2, 2p5. So its s orbital is filled, and 2 of the p orbitals are filled. The only orbital that is allowed to bond is one of the p orbitals. So that's what we'll get here, is we'll have a p orbital. Let's say this is a fluorine, and so one p orbital is going to be here. So there's a sigma bond. Here's this fluorine. It's going to have another one, a p orbital there. And then here's a fluorine here, another p orbital there. So we can label these bonds here as sigma bonds, right, direct overlap, between the bromine's sp3d hybridized orbital and the fluorine's p orbital. Now we're going to do the hybridization and bonding scheme for xenon tetrafluoride. So we have 8 electrons from xenon, 4 times 7 valence electrons from fluorine. So we have 36 valence electrons. So we'll draw xenon, F, 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 F. So there's 8 electrons, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So we have 6 domains, which is going to be sp3, d2, right? 1 from the S, 3 from the P, 2 from the D. So how to draw this is we're going to, right, this is octahedral. And we have 2 lone pairs, meaning we'll just do those on the top and the bottom. So let's get started drawing. We'll draw our xenon. And then I'm going to try to draw it. 3D is really hard. Luckily for you, I will not make you draw these. But we'll do an orbital there, an orbital coming out of the page. This one's going back into the page, in front of the page. And this one will be on top and bottom. So this will draw with the lone pairs on top and bottom. That is these guys here. We already did fluorine on the last one. We know that they have p orbitals. So here's a fluorine here. Here's a fluorine here. Here's a fluorine here. Here's a fluorine here. And here's a fluorine here. So we get sigma bonds on each of those fluorines. So we'll draw sigma between xenon's sp3d2 and fluorine's p orbital. Okay, on the next ones I kind of want you to draw them. I do need to give you the Lewis structure for acetaldehyde. Acetaldehyde looks like, it has a formula of CH3COOH. So it kind of looks like, the skeletal structure looks like this. CH3COO. Nope. It's not COOH, it's just CH. So we'll have that be an H. Okay, so these, I would give you this kind of formula because it's pretty tricky. to get at this point. And just knowing that, we can already see that this carbon here is tetrahedral, right? 4 domain for electron groups, so that means it's going to be sp3. This carbon here has 3 electron groups, so we know it's going to be sp2 hybridized. Cool, so let's draw each carbon. So we have carbon, carbon, oxygen, hydrogen, hydrogen. Well, we'll have to draw those in a minute. Okay, so with this carbon here, we have sp2 hybridized, so that looks like a trigonoplanar. So I'm actually going to have to draw that carbon a little further out over here so it can bond. Now this carbon is sp3 hybridized, so we're going to have one here. We'll do one here, one into the board, and one out of the board. Trying to be like a little tetrahedron. Okay, those are our hybridized orbitals. So now we can have our hydrogen atom connect to each of those and to this one. And our oxygen we drew earlier, it's going to have one p orbital that can will do the sigma bond. Hydrogen has the s orbital, so we'll have those sigma bonds here. Let me erase this random hydrogen. So we have quite a bit of sigma bonds. Now this carbon right here, it is missing a p orbital, right? One of the p orbitals didn't get hybridized. So we're going to draw it coming out of the board. That's actually going to be really hard. Out of the board and into the board. And this oxygen also has one going out and in. So right here we have a pi bond sitting on top of that sigma bond. And here we have a sigma bond. So we'll label that sigma bond between carbon's sp2 orbital and oxygen's p orbital. And then we have the pi bond here, again between carbon, so between carbon, but carbon's unhybridized p orbital, and oxygen's p orbital. Cool. And then we have this bond here between carbon's, sigma bond, right, direct overlap between carbon's sp2 orbital and hydrogen's s orbital. And then we have this sigma bond here between carbon's, sigma bond, carbon's sp2 orbital and the other carbon's sp3 orbital, right? Here's an sp3 and here's an sp2. And then all 3 of these are carbon sigma bonds between carbon's, the other carbon's sp3 orbitals and hydrogen's s orbital. So just being able to look at these and label them is going to be key. Now we'll do hydrogen cyanide. Is connected like this in that order. So we have one valence electron plus 4 plus 5, so for a total of 10. Remember, hydrogen can only form have 2 electrons. So we'll have 2, 4, 6, 8, 10. Carbon is missing its octet. It actually needs quite a bit. It needs 4 more, so we're going to take both off of the nitrogen and form triple bond, double and triple. So 10 electrons are on it, and each one has an octet, carbon and nitrogen. So we can see that the carbon only has 2 electron groups on it, meaning that is sp hybridized. And we can see that here this orbital is going to be part of it, and this one. But the extra bonds here are going to be from pi bonds. So let's draw carbon, nitrogen, and hydrogen. And we can start off by drawing carbon's sp orbitals. So if there's one sp orbital, here's another one. And then we know that carbon is going to have a p orbital going up and down and one going in and out like that. Okay, so there's carbon, it's done. We know hydrogen has an s orbital. Now nitrogen, let's just draw nitrogen's configuration. So we have 2s2 and 2p3. All right, so now we can see that all three orbitals for nitrogen can get used up. So let's draw those guys. We'll have all of them are p orbitals. So the one that's going to be in line with the carbon's sp orbital is going to form a pi bond. We'll have one going up and down and one going in and out. So we'll have a pi bond going between our y-axis, a pi bond going with our z-axis. So we have pi bond between the carbon's p orbital and the nitrogen's p orbital, and we have that twice. Then we have a sigma bond here between carbon's sp orbital and nitrogen's p orbital. And then we have another sigma bond here between carbon's sp orbital and hydrogen's s orbital. Alright, so now let's do another one. So many practice problems. We're going to do ethene. Ethene looks like this if you draw the Lewis structure. Okay, so we can look at each of these carbons. Both of them it's symmetric, so both of them will be similar. They both have 3 electron groups on them, so 3 groups means 3 hybridized orbitals. So 1 from S, 2 from P for sp2 orbitals. So let's start with our carbons, then our hydrogens. We know that it's going to be trigonal planar because there's 3 groups, so we can draw them at that 120-degree angle. So starting with carbons, sp2 orbitals. So here's sp2, 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 sp2. Already we can see an overlap. We know hydrogen has a 1s orbital, so those will have that overlap. Good. Now each of those carbons has 1 p orbital, right, that didn't get used up. We only used 2 of them. So it's going to go up and down out of the board. I'm just going to draw it like that for the ease of paper and 2 dimensions that we have to write on. But it would go above and below the plane of the molecule. So each of them have a p orbital, and when they line up like that, they will form a pi bond. So we will label it. I encourage you to try labeling it on your own. We have sigma bonds between carbon's sp2 hybridized orbital and hydrogen's s orbital. And that goes here, 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 and here, all 3 of those. 4 of those, sorry. We have this sigma bond between one carbon's sp2 orbital and another carbon's sp2 orbital. And then we have a pi bond, a single pi bond between one carbon's p orbital and another carbon's p orbital. All right, last one. We're going to do it for carbon dioxide and this triiodine molecule. So for carbon dioxide, we've already drawn the Lewis structure many times, looking like that. Okay, so we know that carbon here is linear. It has 2 electron groups on it. Linear meaning it has one hybridization from S and one from P, so being sp hybridized. So we have 2 of those orbitals. We know it's linear, so I can already draw it oriented linear. So this carbon there's one sp, there's the other sp orbital, and then our oxygen atoms have, remember it's 2s, 2p, 4. So we have this orbital and this orbital, p orbital, that are able to bond. So we'll have one going on the y-axis, and then one going on the the y-axis. And then this carbon has, actually I'm going to have to draw that differently in a minute because we need it to align. So we'll draw one going up. This carbon has a p orbital going up and a p orbital coming in and out, right, to kind of make space. So for right here already we can see that we have a sigma bond going on. So both of those are the same. Sigma bond between carbon's sp orbital and oxygen's p orbital for both that and that. Then this oxygen has an let me do red. This oxygen on the right lines up vertically, so there's that pi bond. Now notice this carbon has the other p orbital going in the z direction, in and out of the board, meaning that this oxygen on the left needs one to go in and out of the board, so that way it will line up parallel. So both of those, one's going on top and bottom, and one's going side to side like a big hug. And so they're not going to be like exactly the same orientation. They actually are a little, like they're rotated by 90 degrees. So both of those are pi bonds between carbon's p orbital and oxygen's p orbital. All right, last thing. This just says what's the hybridization of the central atom of I3 minus. So we're going to have iodine has 7 valence electrons times 3 atoms plus 1 extra for the ion. So we have 22 valence electrons. When I draw this, I'm going to draw I. We have 2, 4, 6, 8 with the bond, 10, 12, 14, 16 with the bond, 18, 20, 22. So we can see on this central atom, we have 1, 2, 3, 4, 5 electron groups. So 5 electron groups means we need 5 orbitals. We know that's trigonal bipyramidal. 5 groups means we need 5 orbitals. So 1s, we use all the 3. So right now we have 1, 2, 3, 4. We're going to use 1d. So sp3d hybridization. So just like other theories, this one has its shortcomings. Valence bond theory helps us to predict many properties better than Lewis theory. It helps us to we can do the bonding schemes and talk about bond strengths and bond lengths a lot better, and rigidity. But there's still some issues. It doesn't deal with magnetic behavior. It doesn't explain that at all. And also it kind of presumes that electrons are localized, that they are stuck in place between 2 atoms. And so it doesn't account for delocalization, which happens especially when we have resonance structures. So that is something we have to consider moving forward, and we would do that with molecular orbital theory, which we will not touch in this class, but you could read about it, and if you take organic chemistry, you will talk about it.